An SAP enterprise environment operates as a single, connected organism. They rely entirely on a constant, complex exchange of operational data to function. The architectural backbone enabling this cross-landscape communication is the Remote Function Call, or RFC. Looking at this node map, the glowing bridge connecting these systems represents the CPIC protocol. CPIC acts as a universal translator, taking data from the source, formatting it, and ensuring readability across internal SAP and external platforms. But data exchange environments are volatile. Networks experience latency, servers require restarts, and connections drop. Relying on a single communication method across the entire landscape creates bottlenecks. To solve this, SAP engineers developed 4 distinct RFC connection types, each designed with specific constraints to handle different types of system failure. These 4 RFC mechanisms provide the technical toolkit required to manage system-to-system communication across a complex enterprise landscape. We begin with the baseline standard, Synchronous RFC, or sRFC. In this diagram, you see the strict requirement of sRFC. Both source and target systems must be online. The target receives data and fires a definitive acknowledgement back. This creates a halt and wait mechanism, locking up the source system's resources until that acknowledgement arrives. The vulnerability here is obvious. Target systems experience sudden outages or severe network latency. When that return acknowledgement never arrives, the source system is left hanging. The active work process shifts into a stalled sleep mode. These sleep states tie up critical background work processes on the source system. They consume memory and CPU capacity without making any actual progress. Because of this severe resource drain, sRFC is heavily restricted. It is primarily reserved for scenarios where a graphical user interface relies on an immediate, dependent result to render the next screen for a user. The architecture requires a mechanism that doesn't hold the source system hostage to the target's uptime. sRFC guarantees absolute data consistency through direct acknowledgement, but it enforces a dangerous architectural codependency between servers. To break that codependency and free up source system resources, SAP uses Asynchronous RFC, or aRFC. This protocol operates on a strict fire-and-forget delivery model. Notice the difference in this diagram. The source system fires the data to the target and demands 0 acknowledgement in return. By removing the wait state, the source system's work process is instantly freed to execute other tasks in parallel. Let's apply the exact same failure condition from before. The target system suddenly drops offline. The source keeps firing. The packets hit a dead end and disintegrate. The data is permanently lost, and the source system receives 0 error notifications. Because there is no verifiable integrity, you cannot run financial records, master data updates, or critical transactional payloads through an asynchronous connection. aRFC optimizes processing speed and resource independence, but it completely sacrifices data reliability. To solve the severe data loss vulnerabilities of aRFC, administrators rely on Transactional RFC, or tRFC. tRFC operates asynchronously, meaning it still frees up the source system's resources, but it layers on a strict tracking and database buffering mechanism. Look closely at this outbound payload. Before the data leaves the source, the system generates a transaction ID, or TID, stamping it directly onto the packet. That TID mathematically guarantees that every single payload is a unique, trackable entity. Once again, the target system goes offline. Rather than disappearing into the void, the packet detects the failed connection and immediately reroutes. It is held safely in a specialized buffer table within the source database. An automated scheduler program runs in the background at 60-second intervals, constantly pinging the target to see if it has recovered. The moment the target system becomes available again, the scheduler automatically releases the buffered packets, completing the data transfer. If a target system receives a packet it has already processed, it cross-references the TID, recognizes the duplicate, and safely rejects it. In this view of the SM58 transaction screen, we see exactly how this is managed. This interface tracks the status of every single pending TID. Basis administrators use SM58 daily to investigate stuck transactions, identify network locks, and manually reprocess data if the automated scheduler fails. tRFC achieves the optimal state for asynchronous communication. It guarantees delivery exactly once, eliminating both data loss and data duplication. tRFC has one remaining architectural vulnerability. It guarantees delivery, but makes absolutely no guarantees about the order in which those packets arrive. If an ECC system sends a payload creating a customer record, followed by a second payload assigning an order, the master record must arrive first. If the order arrives before the customer exists, the transaction fails. qRFC, or qRFC, is the specialized extension designed entirely to enforce chronological fidelity. In this diagram, you can see how erratic tRFC packets are corralled and forced into a strict first-in, first-out pipeline. This chronological control happens on both sides of the connection. Outbound queues leave the source system, and inbound queues enter the target. The outbound scheduler, configured via transaction SMQ1, regulates how data leaves the system based on predefined remote destinations. On the receiving end, the inbound scheduler in SMQ2 catches the incoming data and processes it based on specific registered queue names. To actively monitor these pipelines, administrators rely on this split view. SMQ1 tracks the outbound queues, and SMQ2 monitors the inbound queues. Because chronological order is absolute, if a single transaction at the front of a queue fails, the entire pipeline halts. Nothing else moves until an administrator clears the error. qRFC purposefully limits processing speed and system independence to achieve an unbreakable chronological sequence. Looking at a healthy SAP landscape from a macro perspective, we see all four protocols operating simultaneously: real-time codependency, asynchronous speed, guaranteed database delivery, and strict sequential queues. The protocol you select depends entirely on the data requirement. You must weigh whether the transaction demands an immediate UI response, pure processing speed, guaranteed exact delivery, or strict chronological order. Diagnosing complex system integration failures requires identifying both the data payload and the specific protocol managing its transit. An SAP infrastructure is ultimately only as resilient as the specific RFC mechanisms engineered to connect it.